Welcome back to Clipboard Electronics. Today I'm going to go over the most basic thing everyone needs to know when using microcontrollers, Arduino, Raspberry Pi, anything. This LED circuit right here, which is going to show up over and over and over again in your microcontroller journey. In the video I'm going to go over the basics of the circuit and how it works. I'm going to cover the code for fading the LED, which is very simple in the case of Arduino. And I'm going to have a nice visual demo of what's going on when you're doing PWM. If we take a look at this circuit in two halves here, the first half of the circuit is really just powering the Arduino. I've got the plus of the battery going to VIN on the Arduino here, and I've got the negative of the battery going to ground on the Arduino. And this also establishes the common ground that we'll use for the entire setup. Now, the second part of the circuit starts from this PWM pin right here, and it will dump current through the LED and the resistor down to ground anytime that there's a voltage on this PWM pin. Now, that current that I mentioned is coming from the Arduino pin, and we call that sourcing current from the pin. It's very important not to try to source too much current from a single pin or from the whole board itself. And those limits that we need to keep in mind are the Arduino Uno can only source 40 milliamps per pin and 200 milliamps for the whole board. And the micro that I'm using today can only handle 20 milliamps per pin and 50 milliamps from the whole board. So for example, in the old video where I did the LED strip that had like 100 LEDs on it, and it ended up pulling about 2 amps, I could not hook that thing up directly to the pins on the Arduino. And that video actually ended up being mostly about how did I power that LED strip that needs 2 amps of power. So it's very important to pick the right resistor for this circuit so that you don't get too much current coming from the pin or from the Arduino itself. And when you start adding up LEDs, that becomes even more tricky. In my case, this LED can only handle 20 milliamps. So that's my absolute upper current limit. But in reality, these LEDs tend to be at their maximum brightness, at least to my eye, when they're getting about 10 milliamps. So we have some wiggle room to play with here. Now, since I know the voltage over here is 5 volts, and the current that I want is about 10 milliamps, it's really easy to calculate the resistor I need using Ohm's law. Ohm's law is a really simple equation that is usually written as V equals IR, which is voltage equals current times resistance. Now this allows, if you know any two of these numbers, to calculate the third. Now in our case, we know the voltage and we know the current that we want, and we want to calculate the resistance. So we rewrite this by dividing both sides by I, so we get R equals V over I. Now for our circuit, we have 5 volts and we want 10 milliamps. So it's really easy. Resistance equals, now for reasons I won't explain, the LED in the circuit basically subtracts 1.8 volts from the circuit. So we write 5 minus 1.8 for the voltage, and that is divided by our current, which is 10 milliamps. So for 10 milliamps, we can write that as 10 1,000ths, right? Which is the same thing as 1/100th. So if you do a little Common Core math here, what you get is, alright, 3.2. And then this business here is really just times 100. Because remember, dividing by something is the same as multiplying by that thing upside down. And this is really easy. Just move the decimal point over 2 places. You get 320. So the resistance we want is 320 ohms. And it turns out, by looking at my box of resistors, there is a 330 in there. Now if I plug this back into Ohm's law, just to double check, we find out that this gives me a circuit with 9.7 milliamps in it. Which is perfect. That's just what I want. So why did I go through all that? The reason is because this is a digital pin here. And that means that it is always either 5 volts or 0 volts. It's never in between. So my circuit is always going to see either 10 milliamps going through here or 0. Never in between. There's no way that I can get 5 milliamps out of this circuit. It's just not going to happen. So if I want to control the brightness of this LED, what I have to do is take advantage of that digital ability to switch that 5 volts on and off really fast. And that's what PWM does. PWM switches the voltage on and off really fast for differing amounts of time in order to get a power level that you want here. Alright, if I hook up this nice little oscilloscope that I built in a previous video, you can see what's going on across the LED. First, it's kind of cool. You can see the 1.8 volts of drop across the LED. But you can also see all these pulses. So these pulses of 1.8 volts, all the same, are getting skinnier and wider as you go up and down in the fading cycle. You can see when the LED gets dim, they get small. When the LED gets bright, they get bigger. Now I'm deliberately fading not to 100% and 0 here so that you can see this. But this is how we control the power level. And we call that the duty cycle. So if these peaks are 50% of the distance, that would be a 50% duty cycle. And even though the current level in the voltage is constant, the power that we'll get through the LED would be 50% of the total power that we could get if this was on all the time. So that's how we can control power levels using digital pins, by controlling this PWM signal. Now this signal is 970 Hertz, so 1,000 times per second. This is going on and off. It's not going up and down, it's going on and off. So keep that in mind. And this becomes important when you start running motors and stuff using PWM signals. Many RC pilots have found out this lesson the hard way by frying their motor, thinking they could run at 50% throttle. You can't do that. 50% throttle means full power for 50% of the time. So now that you understand all that stuff about duty cycles and PWM, you can look at this code and it's really easy to understand. I start out by first setting the pin mode. Now you don't really need to do this because analogWrite sets the pin mode, but if I do it in the setup, it only happens once and we don't have any mistakes of having that pin accidentally connected to input for any period of time. Now as you go through the loop here, you can see I'm setting up a fade value and I'm just looping through in steps of 5 from 20 to 230. And writing that onto the pin using analogWrite. Delay a little bit, do it again. Delay for a second when I get to the maximum, and then I fade backwards again. Delay 1 second, do it all again. Now yes, I am using delay here because this is just example code. You should not use delay in real code, but it works for this example. So the meat of this code is this analogWrite function right here. So analogWrite will set the PWM on this pin to whatever duty cycle you send in here in terms of 0 to 255. So if you want a duty cycle of 50%, you're going to use 128. If you want a duty cycle of 10%, you'll use a number around 25. So 0 to 255 here. That's what you can control. And it really is that simple. This analogWrite instruction is all you need to know to control the PWM duty cycle on a PWM pin. Now, I know that seems like it was a really long explanation for a very simple circuit and a very simple concept. And yes, it was. But it's critical that you get this right, because this is going to come up over and over again. A 7-segment display, for example, is really just 8 of these put together. You know, and if you have a 4-digit 7-segment display, that's what? 32 of these suckers? So you really have to understand this, because you're going to use it over and over and over. And understanding the way digital pins work, as far as only being on or off, is really important. That's what digital write does, but that's also what analog write does. It doesn't really write an analog value in the case of these PWM pins. So thank you for sticking around towards the end. I know this has been kind of a long episode of Clipboard Electronics, but armed with this knowledge, you really can get a lot of different things done. So let's go do some physical computing.